going to talk about indexing, segmenting, and in general handling video data using speech recognition and other techniques that Viraj is well known for.
Thanks, Sanjeev. So this is the pointed title, which hopefully will become clear as I go through. Those of you who have heard me talk before will recognize this picture. This is my favorite picture, and really sums up one of my key interests, and one of the things that I keep coming back to and keep trying to address. And that's the fact that in today's world, we're bombarded by information from all sides, and this is symbolic. What we're working toward as language researchers, as speech researchers, as video researchers, is to enable this person to sit relaxedly in the chair and watch all of these screens at the same time. So what we're doing is, rather than splitting the attention to all these screens at the same time, is telling that person where to look and when. So we're cutting up each of the signals, indexing them, finding out what that person's interested in, and saying, look at this screen now, this is what's most relevant to your interest. So that's what we're doing. And for Raj, our research goals are manifold. I should say up front, due to various vagaries of funding, a lot of what I'm talking about is planned and in the works. So a lot of this I don't have definite results with numerical values, but we have a lot that we're working on and a lot that we will be working on over the next couple of years. One of the first goals is to demonstrate the feasibility of large-scale, real-time multimedia data harvesting. We have a system running in our lab that daily captures 6 television networks, 54 different news broadcasts in 3 different languages. So every day we're capturing 54 news programs in English, Arabic, and Mandarin. And we're working to develop and integrate multilingual language processing tools. So we don't just store these video programs, put them on videotape, and put them on the shelf. We want to process them. We need multilingual language processing tools to see what's going on in those broadcasts. And we're working on trainable audio and video processing techniques so we can take advantage of all this wealth of data, the different information streams that come across in video. So we're looking at video, audio, and language processing. And in the process, we're integrating new technologies into an existing plug-and-play architecture. So what we have is a nice API where we can take someone else's software, write a couple hooks, and run that on the 54 broadcasts that we're capturing every day. So currently what we have is speech recognition, named entity. We'd like to put language ID in there. And machine translation, topic classification, different acoustic event detections. Also video and image processing, face ID, on-screen logo detection, OCR on the keyframes of the video, color frame detection, so we can see transitions between different video signals. A really simple reason why we're focusing on multimedia rather than just audio or just video or just text processing. This is from some research done at the University of Pittsburgh where they found if someone reads, then they remember about 10% of what they read. So if you ask them a week later, a month later, they remember a little bit about what they read. If they hear it, they remember a little bit more. If they see it, they remember even more. But if you put all those together, they remember about half of what they've seen and they've heard within a certain time window. So this video image combined with this audio signal is really important for getting people to remember what they've seen and heard. And ultimately, we'd like to move toward the experiential learning where people are talking about what they've seen and heard, teaching others, and of course then they remember a lot more. But that's our motivation for processing multimedia. And this is another nice figure. That this, sure.
This is probably exaggerated. I mean, like see and hear is what you see on the TV. I don't think that anybody remembers 50% of what they've seen on TV.
I think it depends on the type of signal, the type of audio and video experience that the person has. I mean, you're right. It's not just a set number that any seeing and hearing experience you remember half of it. But there's definitely results that show if you combine these, if you combine seeing something and hearing it, you remember a lot more in the future.
So this particular paper or experiment, was it like factual information? So you were told that so-and-so is the capital of so-and-so, you either read it or you hear it?
Right.
And then after a few days, somebody asked you, do you know?
They looked at different kinds of experiences, TV, lectures like this, versus just listening to the audio track or reading a journal article.
And I guess what I'm trying to ask is, what does it mean to remember something? Do they have to just learn some fact from it, or do they have to reconstruct what was said or done?
I think they focus on facts,
Okay.
or summaries, the basic gist of what happened, what they saw and heard. So this is the television broadcast spectrum. And this is nice because it shows the relative proportion of what's being sent in a video signal. And you can see that the audio spectrum is this thin part over here that's about 1/4 of a megahertz of broadband bandwidth. You get about 23 times the bandwidth for the video signal. Now obviously there's compression issues and not everything in a video signal is really interesting. Thanks. But really, there's a lot in there, a lot of information that we'd like to take into account. If we strip the two apart, then we're losing that correlation between the image that we see and the sound that we hear. And this is frequently what happens, that we get fragmented research, and that the video is frequently sent off to the video processing community, and audio is sent off to the audio processing community. And really, we're talking about 4 research communities here. You've got the raw video processing community. You've got the image processing community that takes just a screenshot and runs OCR or object recognition on that screen. You've got the raw audio processing community that are detecting certain acoustic events, raw acoustic events. And then you have the language processing community that's looking for the language artifacts in that audio. So we've got 4 different communities with very often these bars between them, so they often don't talk to each other very much, and they argue among themselves within the community. So one of the things we're trying to do is take advantage of results from these 4 research communities, combine them into a single research prototype so that we can get all that information out of the audio and the video. So this is a list of the technologies that we're either currently working with or we want to integrate into the FlyTap system, which is a prototype developed under the DARPA TIDES program for video, text, and audio processing. From the video community, we get scene detection, transition between scenes, commercial detection, image processing, face recognition within the screen, logo detection, so you can see what broadcaster logos in the screen, keyframe OCR, so if there's text on the screen, what's that text, and can you pull that out as metadata. The audio processing community, where's their silence, where's their music, how does that interplay with the other signal that's coming across. Speaker ID, language ID, speech recognition, machine translation, information extraction, basically any language technology really helps in this processing, and since that's what I'm most interested in, then I want to get as much of that as possible into. John?
Can you tell us what you have now and what you need? What are your biggest gaps?
One of the biggest gaps is language ID. So we're basically dependent on knowing what language the signal is that's coming in so that we can have the right switches set for ASR and NT and all the other language-dependent processing. And we've had a lot of interest in putting language ID at the front end so that for arbitrary signals coming in, there's just an automatic switching and filtering toward the right components. Speech recognition in MT, we have ASR for Arabic and Mandarin. It can always be better. So we'd be happy to put different components in. MT, we have Arabic to English. We'd love to have Mandarin to English, or any other languages that come along the pipe. We're always looking to put new languages in. These are just the 3 that are focused on in the Tides community. So basically any new language and audio processing components. One that we're working on now in the video processing is play detection. So if you process sports events, that's a different kind of video than broadcast news. And there's some nice research done at Sharp Labs in Washington State on detecting where the plays are within an event. So that you can either skip over replays when you index it, or you can skip over the baseball players spitting and scratching and doing the things they do for about 2/3 of the game. So they've shown you can compress a 3-hour baseball game into about 40 to 50 minutes of action by automatically detecting where the plays are. We'd like to put ASR and language processing information extraction on top of that so we can label those plays as they're put on. So basically we just have this nice big sandbox where we're plugging toys in and seeing what we can get out of the video signal. This is the flow of the VITAP system. We have satellite TV coming in straight off the dish. For English language broadcasters, Al Jazeera in Arabic and CCTV in Mandarin. We have 3 different boxes processing those. The ASR systems are on separate boxes for CPU sake. So we have 6 machines processing 3 satellite feeds. And I'll show you Video Logger in a minute. That's really the key component that sucks in the video stream, indexes it, and runs all of these video and audio processing components on it. And Control Center's the software that tells the video logger when to turn on and when to turn off, when the broadcast starts and stops. And we suck all the metadata out of the signal, throw it into the database, and do retrieval from a web browser. And then we're also, within the Tides community, making this available via SOAP server to other Tides participants. So BBN and MITRE are using the data that we're capturing and processing in their individual text and audio processing systems. Textually, this is what we're doing. Multilingual video channels. One of the key elements here is it's built on commercial software. So the base of it is commercial software that's stable and supported. So we can depend on that. We don't have to worry about it going down and not being able to come up. It's been around for 5 or 6 years now. It's productized. It works really well. So we use that as the base, and then we take the research prototypes, the research plugins, we stick those in there and see what happens. So we have this plug-and-play architecture. The audio and video streams come through. We pass those out to the different components, and they pass back the information that they've pulled out. And this is all the stuff we're working on now. The user interface to make it easily accessible for the people that want to have access to this news. Alerts, so if something happens in the news, then the users know immediately, and they know to go right to the video channel. And segmentation, which I'll talk about in a minute. So this I pulled actually from our marketing department, but what I'm most interested in is the research part down here, which you can tell is less refined and less slick looking. Basically, there's this video logger that brings in video of any kind. Verizon's basically agnostic when it comes to what kind of video. Real video, QuickTime, MPEG, it all works. Similarly, we can encode it as any kind of video. And right here is the media analysis stuff. So the video and audio processing, natural language processing, the MT, the segmentation. This all goes in as a plugin, and we get out either a flat file, an XML, or something that goes into an Oracle database and can be retrieved. It can also go into an information retrieval system for retrieval of the metadata. So let me show you what this all looks like. This is an Arabic broadcast that I just have stored here, and we can look in on the live capture in a minute. On the left here we have the keyframes, and basically the system will snap a keyframe whenever there's a significant change in the video. So in the opening segment it happens a few times a second. When the anchor's sitting here, then it might happen every 10 or 30 seconds. But these are the keyframes that go through the broadcast. Basically, if you look at the keyframes, you can get a general idea of the flow of the broadcast. And here we have the media analysis components. Each of these tabs down here is something that's being run on that audio and video signal. So right here is the output of the speech recognizer. Everything that comes out is time-stamped in both milliseconds and SMPTE, which is the broadcast standard. So this is at 1 minute and 25 seconds and 13 frames, this word was spoken. So every piece of metadata that's extracted from the video or audio is time-stamped like this. So it's easy to correlate what's going on at what time in the broadcast. We can pull out any part of the data and play the video for that. So it's really easy to look at the metadata, see what's happening. If it looks interesting, pull up the video for instant gratification. Other things that are happening in here, we have Face ID. This is just a partnership that we have with a Face ID. This is, I think, Visionics. And you can see you've got a face, and in this case it's an unknown face. The Face ID is really dependent on the library that's fed to it, just like speech recognition is dependent on the vocabulary. If you don't give it the face, if it's not in the library, it's going to be unknown. One of the things we've done in our research lab is improved on the black box that we got from the Face ID company. And we noticed that there were a lot of faces that thought it was recognizing that weren't faces at all. And we did some work in how to pull apart the screen itself and really separate what's a face and what's not. So it's not working on what face is it. It's just whether it's a face or not. So this software in particular finds a lot of non-faces. So what we did is looked at the dimensions of the eyes that the software was giving us, the corner of the left eye, the corner of the right eye, and just did a little calculation. If it didn't make sense for that to be a face, then we called it a rejected face. So these are the kinds of things we do to improve the processing. But for the most part, we get faces, and most of them are unknown faces, but at least we know there's a face there. Let's see, there's scene cuts, so when it goes from a scene of one type to another, then it'll tell us, and this is really useful for segmentation, so that we know if there's a long period of something happening and then there's a cut to something else, then that's probably a different segment. Over here, we've got the machine translation of the ASR, which understandably is not that good because we've got errorful ASR being piped through MT, and it's, for the most part, word soup. But for filtering purposes, soup's good enough because you can pull the words out of the soup and you can get an idea of what it's about. So, Lebanese, Beirut, casualties, universities, you can get a pretty good idea of what this is about, even though you can't read it per se. You can't read it as a sentence. So that's very useful. We've got named entity software running on this, so we're pulling out the Arabic, persons, location, organizations, and we're also doing machine translation of those. So if you just look at the entities, then you can really get a good idea of what it's about. Jerusalem, Hamas, Ramallah, pretty clear what this segment's about. So that's the canned example. Let's look in, like I said, we're capturing 54 broadcasts daily, and we can pull up what's happening on the Arabic capture machine right now, and hopefully there's a broadcast being captured to the beauty of VNC. So this is the same video logger I just showed, and it's you can see it's moving. This is actually capturing as we speak. The ASR is spitting out words. These are the keyframes that it's capturing, and then if you click across the bottom,
It's spitting out words, but not it's segmenting them, but not translating them.
no, it is translating them. So that's the word track right there. We can look over at the translation track. So this is the translation that's coming out of that
So it's
right now.
coming out even.
Yeah, so this is all real-time processing. There's about a 1 to 2 minute delay on the ASR because it takes a while to grab the first segment and run that through. But the ASR is running real-time. It finishes a couple minutes
Where do
after.
you get the ASR and that you wrote? Because
This particular one is the BDN system.
and the translation.
The translation is AppTech. So it's
Can you go to
just,
the bottom of the screen and see how fast the translation comes up?
sure. There's a slight delay because we're actually, the VNC goes out to California and then back to our lab in Boston.
Okay, so this capture is happening in California?
No, the capture's happening in Boston, but this window in our VNC servers in California. So you can see, it's a little bit behind because the keyframes are at 38 minutes. The translation's at about 34. The translation has to wait for the ASR to run, so that gets fed to the MT, but it runs at real time once it gets the signal. So that's the real-time capture that's going on.
What's the Arabic error rate?
Actually, you guys probably know this better than I do, what the current error rate is,
I guess around 15%.
right?
1.5.
1.5.
15% for the broadcast news
For Al Jazeera, it's about 23.
23.
23.
Much higher.
So it's in the 15 to 25 range. The broadcast news is obviously better than telephone speech and a lot of other channels. But I can't read it, so I can't really judge how well it works. I know that the output of the translation is usable for retrieval purposes, and that's really what we're interested in.
Do you have speaker ID in there as well?
Yeah.
There's no button for speaker ID, but is that currently implemented?
Yes, and that's part of the BDN. It's over here. Actually, speaker ID is something that's provided at the end of the broadcast, so that's not real time. So that'll fill at the end of the capture. I think we actually are running a library against this now, so we might be able to see some recognized faces.
Recognize faces.
Right. So there's the face library that the software is comparing the faces it sees against. And if it matches, then it'll output the name.
So how many people do you have there?
In the face library, probably 50 to 100. Most of them are the best that we can do at putting a name to like sports anchor or news anchor number 3, because we can't actually transcribe the name of the person. When they say, I'm so-and-so, welcome to
You
midday.
can't do it because?
Because we don't understand Arabic.
Oh.
So,
But is there a way to get it from the text? You know, often the name appears.
yeah, but again, we'd have to be able to read Arabic to transcribe that, to put that in the library. I'll talk about that later, actually, because that's something that we're working on. So that's the video logger, and that's what we're running on all these broadcasts. Let me go give some details about the research surrounding video logger that we're working on. Video logger itself is a product that Verizon sells. CNN is running about 200 of them in their headquarters in Atlanta, but they're using the off-the-shelf version. In the lab, we're trying to beat on it as much as possible and add ASR and MT and as many things as we can to try to break it successfully, usually. So one of the main research goals here is to stress test this kind of software on real-time daily capture. So what happens when we put ASR and MT into the pipeline 54 times a day? 34 hours of audio running through there. All this text, all this video, what really happens? And that gives us 35 hours of video, audio, and metadata to store. It's about 4.5 gigabytes in our current configuration. We're using real video. We've been requested to up that to MPEG-1, which is less compression, which needs more space. So we're going to need about 20 gig a day to store all this video. Obviously, processing all this data requires automated techniques because we're not going to have someone sitting there and saying what's going on. That's why we need real-time storage segmentation, indexing, efficient retrieval of all this data. And I think this is a fertile ground for unsupervised techniques. And it's really nice to have all this information flowing by around the clock. It'd be nice to just have a sniffer there that's pulling really interesting information out of there and learning in the process. One thing I want to show you, just so you don't think we're only doing news, this is a work that we did, that Viraj did for Major League Baseball. It's really relevant to the news segmentation, but it's in a different domain. Basically, Viraj processed all of the Major League Baseball games last summer. So every single game, there's a video feed coming through the Viraj lab. And at the time, they had 20 people sitting there and manually segmenting and labeling what was going on in every single game. So 28 teams in Major League Baseball, 162 games a year. That's a lot of games, and that's a lot of.
They segmenting like this is a hit and this is a.
Right. So if you look at the searchable interface, you can select a team, you can select a player, you can select what kind of play, a home run, any kind of hit. For pitchers, you can select strikeouts. And so this was all indexed and put into the searchable database on the web. So you could pick your favorite player, your favorite team, the kind of play that you wanted, and bring up, and here's Nomar Garcia-Parra batting against Kenny Rogers on August 3rd, and you got a single in the bottom of the first, and you can play this clip. So, in essence, this is the same thing that we're doing with news. So we're taking a whole bunch of data, we're segmenting it into the relevant parts, we're indexing it, and we're making it searchable. Only we want to replace this manual effort. We don't want to force someone to sit there and segment it and label it and take all that time and effort to put it on the web. We want to do that automatically. So what we'd like to do is be able to cut the baseball game into plays and label who's doing what. We'd like to cut the news broadcast into stories and pull out the relevant metadata about what's going on in that story. So back to my favorite picture, 54 broadcasts is about like this. It's nowhere near all of the broadcasts that we could be processing. There are dozens more languages that we could be processing, dozens more broadcasters, countries, feeds that we could be processing, but it's still quite a bit right now, and it's a good stress test for the language processing technology. So, multilingual language processing.
This is the cool stuff that's coming.
What's that?
I asked them, this is the cool stuff.
I'm sorry, we're already past the cool stuff.
Oh, yeah.
That's the boring research stuff.
Oh, my God.
So we want to do automated processing of large amounts of data. This is what we currently have. In English, we're running ASR, speaker ID, named entity, topic ID from BBN and IBM. We're running on-screen OCR. It's a research system from SRI. So this is actually a really cool technology, on-screen OCR. This is, if there's something going on the screen, at the bottom it'll say live from Beirut or breaking news, airplane crash in Zimbabwe. That's interesting information, and it's right there on the screen. And if we run OCR in that, then we can pull that language data, that metadata, and that says a lot about what's going on in that scene. It's related to what's being said in the audio, so we can correlate the two. OCR is not perfect, ASR is not perfect. If we put the two together, we might be able to get better results. Arabic, we're running ASR, speaker ID, named entity, and Arabic to English MT for NAPTEC. Mandarin, we're running ASR and speaker ID. We'd love to be running more languages, more technologies. We just like to throw some more toys in the sandbox and see what happens. So what happens with this ASR MT cascade? This is the original ASR output. At the time, this was 26% error rate. This was November of 2001. Two things to notice in the MT output. First, you can't really read it, although you can pick out keywords. Second, there are untranslated words. And this is actually a nice artifact of MT, is if an MT system doesn't know the word that it's processing, it leaves it alone. It just passes it on in its native form. So the Arabic words that it doesn't recognize and pass through, these are high content words. Because words that haven't made it into the MT system vocabulary are new. New things are interesting. So we want to keep track of these things. So another technology, John asked what we'd like to put in here. We'd like to put John Henderson's transliteration of Arabic to English. Because as it is, this isn't very useful downstream. Because very few people can read this. If we can transliterate it into some approximation of what it looks like, of what the Romanized version would be, what an English speaker would read if they could read that, then we're getting new information. And this is in sharp contrast to what ASR systems do. When an ASR system doesn't know a word, it just guesses at it. It just says, well, the closest one that I can think of that's in the vocabulary is this. Passes it on, and then farther down the stream, you don't know where that word came from or why it was output. You don't know whether it was a guess at a word that is out of vocabulary or whether it was actually correct. And that's information that's lost because the ASR system can't say, I don't know. So another research goal, story segmentation. We need to automatically segment these broadcasts and individual stories because nobody wants to watch the whole broadcast. If there's a relevant segment 15 minutes in, we want to zero in on that. We want to say, look right there. 13 minutes and 42 seconds, that's where it's interesting. So we're extracting this metadata from all the available information streams and using that metadata as features in machine learning for segmentation. Now the problem is the metadata...
Machine learning from a person's reactions, that he likes to look at such and such.
No, this is just segmentation. So this isn't the relevance judgment. This is just breaking a whole broadcast up into the different stories. So what we're doing now is supervised training. We take some broadcasts, someone goes through and says, here are the boundaries, and then we use that as training data for the machine learning. Now, it's noisy features because we're looking at Face ID that makes errors. We're looking at ASR that has a 15 to 25% word error rate. We're looking at machine translation. All the other technologies that we're working with are automatic, so the quality and the accuracy varies. We're throwing all that into a hopper and really trying to do accurate story segmentation. These are some of the features that have been found to be useful in story segmentation. Identification of faces of anchors and reporters. And when an anchor's face goes up, it typically means it's the start of a story. If it stays up, then that means that there's a story ongoing, and that's still part of the original story. Speaker ID, same thing. If there's a speaker change, it goes back to the anchor, that's the start of the story. So there are a lot of these features that have been shown to be useful for story segmentation. In isolation, none of them is perfect. None of them works unambiguously to tell where the start and the end of the story is. Put together, they work pretty well, but they have to be put together in the right way. And when there are errors, then it's harder. So let's look a little closer at what we're getting from these technologies. Face ID, in an ideal world, we get the person's name. That's Peter Jennings, great, we know that. But in most cases, we get this is unknown face number 9. That doesn't help us a whole lot. So we need to improve the face ID, and we need to improve the level of information we get from it. A step in that direction is the confidence. How confident are we that we're seeing Peter Jennings? And confidence is something that we're implementing in just about all of the technologies we're using, in that it's not enough just to say, here's the answer. Here are the words that I heard, here are the faces that I saw, here are the boundaries that I saw. We want some measure of confidence that that's actually what.
But unknown time means that you don't know his name, but he's always unknown time.
That's right. If it can always.
Yeah, but I mean, that's the idea.
That's right.
Same thing, male 17.
Yep. It's exactly the same as speaker ID. If you can consistently recognize someone as male 17, that tells you something. Later on, you can put a name on that. But you're dependent on the speaker ID algorithm to consistently label that person the same. Now, you'll notice all of the information we're getting is text. So we're extracting the metadata, it's turned into text, but it's different kinds of information. In some cases, it's the name of the person. In some cases, it's just a Boolean flag. Yes, I detected something. No, I didn't detect something. Language cues. Here's a catchphrase that usually comes at the start of a story, usually comes at the end. But this is dependent on recognizing the words in that cue and being confident that those are the words that we'll recognize. Same with silences, lip smacks, music. These are all bits of information that we're throwing in the hopper. And what we're trying to do is find a nice technique for combining this diverse information, trying to keep it as real time as possible, because we still want to keep the computation level low. We still want to process these 54 broadcasts in one day, so it can't be something that takes 10 hours per broadcast to segment with these diverse features. And so this is the next hairball that we have to pull apart, is this requirement for real-time alerting. When something interesting happens, how do you throw that over the wall and tell someone, right here is something interesting, when you're getting asynchronous feature availability? You're not getting things exactly at the second. Later on, it's labeled with pretty accurate timestamps. But if you have someone sitting there that wants to know exactly when something happens, they want to know exactly when a home run is hit, or exactly when a certain word is spoken, or a certain topic is brought up in some news broadcast, that really throws a monkey wrench into the segmentation problem. Some of the technologies are available instantly. ASR, there's a 1 to 2 minute delay. Speaker ID and identity is available at the end of the broadcast. You can look at techniques like TDT, which requires all of the text in all of the transcriptions. So that's that goes against this need for the real-time alert, and that if you don't have the features all available right away, then you can't do that alert right away. So what we're doing is a real-time trickle of the key information. You can do this trickle out as soon as the information is available, and then you do the high-quality post-broadcast indexing of all the metadata when it's all available. This is nice because all the features are time-stamped for easy correlation. So at the end of the broadcast, when you have everything, you can look down at any time slice and know exactly what you have at that point. During the broadcast, it's a little more iffy as to whether that's possible. So John Henderson told me that he wouldn't come to my talk unless I threw up a formula. There you go, John. That's a mathematical
What
model.
is the formula?
Basically, it's just
I guess John Henderson is a paper tiger because he didn't know you're going to do it and he was sitting here anyway.
he had faith. The last thing I want to talk about is cross-stream correlation. And this is what I started with, is that if you have research that only utilizes one of these information streams, you're ignoring valuable information in the other streams. So hypothetically, you could have auto vocabulary words in a speech recognition system that are available somewhere else in that signal. And so what we are doing, what we're in the process of doing, is using this available data from all the information streams to improve the overall segmentation and to automatically populate these libraries. So the face ID requires a library of faces with names associated with them. We don't want to sit there and look through hours and hours of broadcasts to look at these faces and say, hey, this is person X, this is person Y, and there's our face library. We'd like to pull that information out of the signal elsewhere. So this is an example of how that would work. We've got our broadcast, we've got different information processors, face ID, let's just say this is an unknown face, it's going to output unknown face number 17. Let's say that name is out of vocabulary for the ASR system. Noreen version is her name, but it's not going to come out as Noreen version, it's out of vocabulary. It's just going to pick something. And this is actually pulled from the data that we have, because Noreen version is still out of vocabulary in the speech system that we're using, even though she's a really common person in all the broadcasts we're using. Speaker ID, if it's not in the ASR vocabulary, then it's not in the speaker ID library. But if we run screen OCR on this, then we could pull out who this person is. And there's a good chance if you've got a person with a face right there, and there's a name across the front of it, that's who that person is. So what we want to do is populate the libraries, populate the vocabularies with this information we pull from another stream. So we can find out who that person is from the OCR, give that back to the face ID, give that back to the ASR system, the speaker ID system. So we don't have to have that manual intervention of someone looking and saying, who is this? I better change my ASR vocabulary and better populate the face library. So this is the idea of cross-stream correlation. Obviously easier said than done. Part of the prerequisite of this is we need dynamic vocabularies and libraries. Current ASR systems usually require a static, predetermined vocabulary. Face ID, speaker ID, most pattern matching technologies require static, predetermined libraries. But we don't have static sources, we have dynamic sources. We have new words, especially names, faces that surface daily. We have changing vocabulary within the broadcast even. If we're talking about news, then we've got world news, local news, sports, weather, etc. If you've ever watched CNN headline news, just about every 3 or 4 minutes, the topic changes completely. And the vocabulary you're using is useless when you switch from one to the other. And we really need dynamic vocabularies to swap in the words that we're more likely to hear. This is just a motivation for moving these systems more toward dynamic libraries and dynamic vocabulary. Part of my dissertation work was on the vocabulary problem in speech recognition and how to account for this. Because there are really two two things that come up. First is you've got out of vocabulary words, but you can't find them because the ASR system doesn't tell you when it doesn't know. But even if you knew that a word was out of vocabulary, how do you find it to put it in the vocabulary of the system? And one of the things I found is that generic word or name lists don't provide wide enough coverage for broadcast news. In the TDT data,
I don't know, what does the word generic list?
Generic.
What does generic mean?
well, these are, well, the census data is probably the most generic example of that. The census data provided first and last name lists for about 90,000 US people, male and female people in the
There are only
census.
90,000 different names in
Well,
the census?
no. They made 90,000 available. That was the top. They pruned the tail off the curve. So these are the most common names in the US.
I mean, in other words, there must be a database which has everything, right? And they won't let you have it.
Privacy is the main reason. So they
I see if you're called Smith, you're not entitled to privacy, but if you're called...
well, yes.
That's the idea.
Basically, if you're called Smith, there are 3 million other Smiths. So if they provide information about Smith,
I see.
then that's not getting.
I see, so these are not just lists, these are lists with links to knowing what their income is.
Yeah, actually, the census will provide demographics on all these.
So you can't just get at the name list.
The full name list you can't.
No, but they would not even sell you or give you the name list. It's, I mean...
Probably not.
You can get the National Telephone Book.
Yeah.
The National Telephone Book has something like 1 million last names.
Right.
Distinct last names. Of course, you're not always sure if it's a person's name or some restaurant or something.
Right. So that's what I mean by generic name list. Intuitively, before I did this work, I would think most of the names that occur in the news would be a common enough name that if you take the top 90,000 names in the U.S., it would be covered. And that actually was not the case at all. That if you look at the auto-vocabulary words in the TDT data from 1998, only 31% of them were in this large list. And if you look at this list, there are all kinds of names. I just can't imagine the names that aren't in there. It's probably 35 variants of Smith that you wouldn't have thought of before. All kinds of variants of Johnson and basically everything. But not everything. You think it's everything. So if the census data doesn't work, then the logical next step is to take some news data from around the same time as this broadcast data. And the TDT data was CNN, NPR, all kinds of broadcast sources from early 1998. So I took the whole New York Times from 1998, January to December. And we even covered the lag if it showed up in the broadcast news there and later in the New York Times. So this was 162,000 words. These weren't just names. These were all the words, all the distinct words in the New York Times in 1998, and that only gave 48% coverage.
It's also very little, 162,000. There are only 162,000 different words in the whole New York Times in 1998. Really?
Yeah.
I mean, we may commonly recognize this, right, with 60,000 word vocabulary. So this isn't even 3 times as much. Amazing.
The TDT2 data already includes some New York Times, right? Or did you exclude?
Not the broadcast.
So this was only the broadcast sources.
But it's surprising.
Right.
Very low, right?
162,000 sounds low.
Didn't Richard Paul have something like 500,000?
Pardon me?
Richard Paul, 2 years ago, he cited like 500,000 different words in this paper.
That was more than one newspaper.
I don't remember, those was not here.
This includes everything that was available from the LDC. I don't know if it has the movie listings or the.
Okay.
So what does the Oxford English Dictionary, the large Oxford English Dictionary have? How many words?
I know. I think it's millions.
Well then, why don't you take that? I mean, why would you take your doubts if you can have...
Well, the Oxford English Dictionary doesn't have the names that are going to be out of vocabulary.
Oh,
in podcast news.
excuse me, so 162 are only names?
No. But we're trying to match names
Yeah.
out of vocabulary names.
But obviously new names come up, like this guy who distributes anthrax, right? He's got a very weird name, I forget what it is.
Right. But that's exactly the point.
I've never heard such a name before.
Like Langford.
Huh?
It's counterintuitive that the names that pop up, really, that's the first time that we've seen
Yeah,
it.
I think that
Just about anywhere.
first time I've seen this.
And so we need a good source to cover those names. The census data doesn't give us that, and the print news sources don't give us that. So that's just the motivation for why we need to do something else. And so one of the solutions to what I'm talking about is that if this anthrax guy occurs in the news, then his name is going to show up somewhere in that news. It's either going to be on the screen, it's going to be in the closed captioning, it's going to be somewhere.
Why don't you use Usenet? It seems like that's sort of an instant source of a discussion about just about every topic. And I bet the word lists there would be much greater even than the New York Times. And it's free.
It's free. It's a little noisier than the New York Times. So you've probably got a lot of words there that aren't words, or that are going to confuse your model. But sure, that's a source. Any breaking news websites, things that just pop up, Reuters, Newswire, those kinds of things. At least for the really relevant people that come up, those are candidates. But if we look at these other information sources that are they're happening at the same time as. So this is looking at if you've got a news broadcast, you don't know yet that there's a new person. So you don't know yet to go out to Usenet or some other source to look for the name. You've got to make a decision pretty quickly about what to do with this new name. And you've got the information right there, so you can grab it. Let's see. I guess it's. Yeah. I had a slide in here that the obvious question that everyone always asks is, why don't you just add all these words to the ASR vocabulary? And why don't you just take, assuming you had perfect coverage, you had a list of words, all these words are going to occur, just throw them in the ASR vocabulary. There are really good reasons not to do that. That you guys can probably enunciate better than I can. But one of the results that I found in my dissertation was that Lewinsky was an out-of-vocabulary word in the data that I was processing. Because before January 1998, not many people had heard of Monica Lewinsky. But Lewinsky with an I was in vocabulary because there was a reporter named Robert Lewinsky who worked for NPR or one of the broadcast sources. So Lewinsky with an I was a really common word in that data. And I really expected that every instance of Monica Lewinsky would just come out as Lewinsky with an I. Monica Lewinsky spelled with a Y. But what happened was only in 23% of the cases that was the case. So only 23% of the time when Monica Lewinsky was in the news, her last name was output as Lewinsky with an I. And the reason for this is simply language modeling. That the context in which Monica Lewinsky occurred were very different than the context in which Robert Lewinsky occurred. And the language model had been trained on Robert Lewinsky with an I. And those bigrams and trigrams simply didn't come up in the same circumstances as Monica Lewinsky with a Y. So it was much more frequent that words like Lewis he, or to just some kind of nonsense word sequence that was phonetically similar to Lewinsky but was not fluent with an I. So that's the simple explanation for why you can't just throw these words in, because even when a homophone is in the vocabulary, you're not guaranteed to get that out. And in fact, you're probably less likely to get that out because of the context. So with dynamic vocabulary comes this need for dynamic language modeling, or at least some kind of intelligent mixture language modeling, so that new words are made more likely and in the right context. So the last thing I want to point out is going back to the data that we're working with. We have a SOAP server. All the 54 broadcasts that we have are put up on the SOAP server. This is a screenshot of BVN's ONTAP system, which you can see down here is pulling up the same kind of, it's pulling the data directly over from VITAP and it's putting it up. And MITRE's doing the same thing with their system in the TIDES program. This is what the SOAP command looks like. It's just XML, so it's really easy to just put together a SOAP query, go out and pull the data over, and use it however you want. Now, one last thing, I wanted to actually show you the VITAP server that we're running. Our first task is to redesign the UI, but for now, I'll just use this one. So this is just a simple search. This is access to 3 months of broadcast of these English, Arabic, and Chinese stories. So you can search for something like Sharon in Israel, which is pretty likely to be in the news these days. And now it's going to go out and find all the automatically segmented stories from these broadcasts. You can see it found 12,000 stories for the past 3 months. The top one's from CNN this morning, a bunch from CNN.
Every picture is another story.
Every picture is another story.
And what are those things called live there and classroom?
These are the different fields that are populated in the database. It's the date, the broadcaster, the news program. So this is today's Al Jazeera News Bulletin, broadcasting country, the language, whether it's live or taped.
Yeah. And what are these things in the columns then?
This is the metadata that goes along with the story.
Like what?
So the things below live
I can't do it, so I can't do it.
Okay.
So the things below live have nothing to do with it being live. They just are
Right.
Oh, I see. That's number one. All right. So
Yes,
what does it say there? I mean,
so this
what kinds of
is,
stuff does it say? Yeah.
these are the names that are automatically extracted from the broadcast: Israel, Kenya, Sudan,
I see.
Happy Mohammed, Iraq, Saddam Hussein, United Nations. This is the...
So this is like name entity extraction.
Exactly. It's named entity extraction with MT. So
Yes,
it's the Arabic entity and the translation of it. This is the full translation of the first part of the story. And then you can play the clip. So this will reach over to the VITAP server, and we'll bring over that.
Network now?
What's that?
Are we going over the network?
This is going over the network and pulling it over from the Verizon server.
شارون أطلق تهديده أمام لجنة الخارجية والأمن البرلمانية في إشارة فسرها المعارضون والسياسيون على أن الهدف منها ردع حزبي العمل وشأس اللذين يهددان بالتصديق.
So that's a simple kind of search that you can do. I don't know what the classroom is. I think that's a bug in the. So you can use this to search for clips on any topic, and it's going to bring up. This one's from today, but it'll go all the way back. Jump up to the 9th page. It's probably yesterday. So that's it.
what kind of commercial approach? I mean, obviously, for government, it's what they want. But
Right.
what kind of commercial applications do you see for it?
One of the commercial applications is Major League Baseball. Really,
Like somebody would like to see every game.
right. Who doesn't want to watch every game but wants to see all the highlights.
But is that big enough?
It is a pretty big market. There are a lot of baseball fans. And then there are other sports, football, hockey, basketball, the World Cup, NASCAR. So any large corporation, sports league, who has a lot of video that they want to make available, make it searchable, make it indexable. The prime market for this kind of thing is news broadcasters, because they have the most video and they have the biggest need to find things quickly. But really, anybody that has a collection of video that they want to make searchable and make available. Yes?
So you mentioned about wanting to have in your research test bed to be able to plug in different types of things. Do you have some form of a test suite or test harness that you can see if new things you put in add value, and if so, what is that, and how are you evaluating when you put things in other than just kind of looking at it?
We have a test suite for each of the technologies that we've used so far.
Like what are they?
It's,
I mean, do you have like pre-marked words for doing ASR,
Yeah.
speaker ID, or pre-segmented
Yeah.
face, things like that?
we've done a lot of ASR evaluation, just the classic NIST style, where you take a held out test set and you run the new engine on it and score it to see how well it does. We've done that a lot with new languages. If people want a Spanish recognizer or a German or French recognizer, just so they get an idea of how well it's working in this context. The Face ID, we have a standard suite. We've evaluated 3 of the commercial vendors. And so if there's a new technology that we need to evaluate, then we put together some kind of evaluation. But it's all formally evaluated.
Well, I was thinking, that's good to hear. The other part, it seems like you were talking about wanting to push into like dynamic libraries, whether it's for face or voice. That's going to get kind of tricky into this evaluation. Have you thought more about what you might do for evaluating with dynamic libraries?
No, that's a good point. No, I haven't.
I had a comment on the Robert Lewinsky, Monica Lewinsky. When you get Robert Lewinsky in your training data, isn't very often Robert Lewinsky saying, this is Robert Lewinsky from...
Yeah. So because he's a reporter, almost all the contexts are, let's go to Robert Lewinsky in Washington. Or
Okay, so it's a couple of fixed anchors and Robert Lewinsky saying Robert Lewinsky. I wonder whether the acoustic models are also too finely tuned to those people.
That's very possible too.
And perhaps if they said Monica Lewinsky, you might even get Lewinsky with an I. Then it gets those 2 or 3 anchors who say Robert.
Right. I don't...
So, because one of the things I've found is that usually the acoustic scores tend to dominate. So just because your language model doesn't like Lewinsky following Monica,
Right.
won't give it enough of a veto to kill. Lewinsky is a long word.
No, but it's the language model because they're monophones. I mean, they are the same. It's the same acoustics.
No, but that's what I'm saying. The acoustics models won't fit because when it's like, let's say only one person says Lewinsky in your entire training data.
Yes.
Several of those triphones, their training data is dominated by this one person saying Lewinsky.
But you share the triphones, and if you glue words together from multiple people saying different things.
Right, but what I'm saying is that very often with complex words, the particular phone sequences that you see are not very common.
That would
That's
have
the
to be
result.
tested.
Sorry?
That would have to be tested in the training data.
But at the same time, there's enough data for them. So when you do your acoustic clustering,
It's the language model.
you can say, okay. No, I'm happy to see that it's a language model because then it gives...
Well, we can't conclude that either, right?
Well,
Actually, this is no speculation.
Yes, it's not.
We don't know
Yeah, of course.
anything.
But my lies
No, because very often when the acoustic scores are just an order of magnitude bigger, if the acoustics like something, most of the time it just gets through or doesn't.
Well, it may be that the monocolor scheme was spoken by so many more speakers in so many more contexts that it wasn't able to.
Because who's that guy? David Brancaccio. And if you break down the broadcast news by speakers, the accuracy in Brancaccio is close to 100%. It's like 95 or something. And it's partly because he's a very articulate speaker, and there's lots of training data from him. And then on top of that, like he's got a fairly particular voice. So although you might think your models are all aggregated over so many people, there are many things which only he says, even the new training. Are there more questions? In that case, we have cookies waiting for us.